In this next section, we're going to dive a little bit deeper into the combustion process that goes on inside an engine. We're going to look at the chemistry of it. And by doing this, by looking at the chemistry, we're going to get a better understanding of what's happening in there and how that relates to that air-fuel mixture that's coming into the engine and how important that is to have the right ratio, to have the right the distribution, to have good mixing in the chamber and all that. We're also going to see from that process where bad emissions come from, what causes emissions, and then we'll talk for a little bit about some of the general ways that we go about mitigating those emissions. So that's how we're going to approach this section. So let's get started first of all by looking at some combustion theory. Let's look at the chemistry of the process. So what's going on? Well, the process that's going on is actually an oxidation process. It's very similar chemically to what happens when a piece of metal rusts or corrodes. So it's the oxygen combining with the original chemical components of that. So it's an oxidation process. So basically we're taking fuel and oxygen into that process. They get mixed, except in this oxidation process is a whole lot faster than steel rusting or something like that. So we have a lot of heat and it happens really fast. And what we really would like to have coming out of that is carbon dioxide and water. That's a clean, perfect combustion. Now we think, oh, carbon dioxide is a greenhouse gas. Yeah, it is a greenhouse gas, but that's the ideal product of this combustion. We'll see some other stuff that's really bad that we'll have to clean up later. So chemically, what does that look like? That equation looks something like this, where my fuel molecules, and we'll see this as we move on, but they're going to be made up of carbon, hydrogen, and maybe some oxygen. And I have question marks in there on the subscripts because different fuels are going to have different components. So more carbons, more hydrogens, whatever. So we'll see that as we go through, whether it's gasoline or diesel or methane or propane or whatever it is that we're burning in this engine. That's going to be the chemical formula for that particular fuel that goes into the engine. And what we want to do is mix that with oxygen. So we're going to have add some oxygen to that in the reaction. And that's going to break up this fuel molecule into the carbon and hydrogens will be separated. The oxygen will get separated out. And then we'll recombine as carbon dioxide, CO2, and water, H2O. So that's what that process would look like, the fundamental process. Now, we can't just put oxygen in the engine. Think about how we get the oxygen in the engine. The fuel's easy. We got carburetors, we got fuel injectors. We've talked about all that technology of how we get that fuel into the engine, but it's mixed with air. We really only want the oxygen, but we're kind of stuck with a little bit more than that. So instead of oxygen, what we really end up with is oxygen and nitrogen. So let's think about what air is when it goes into the engine, and we can break this down. Air has a lot of different things in it. It's got oxygen in it that we want, but it's actually mostly nitrogen. So most of our air is nitrogen gas. And there's a lot of other gases, of course, carbon dioxide and methane and hydrogen and all kind of other gases. But they're just a small percentage, a small component of what makes up the air. So primarily when we're looking at the chemical reaction, we can kind of ignore all of those other gas components. We can ignore the carbon dioxide, the carbon monoxide, and everything else because there's not very much of that. So the primary thing when we ingest air into that engine is that it's made up of oxygen and nitrogen. And there's a ratio or relationship between those two. Again, there's more nitrogen than there is oxygen in there. So the number of nitrogen molecules, the number of N2s, so the number of nitrogen molecules is equal to 3.76 times the number of oxygen molecules, the number of O2s that we have in the air. And we'll use this relationship in some equations as we're balancing these chemical equations and seeing what's really going on inside that engine. So that's one of the relationships that we'll have to remember. So let's do an example. Let's look at this chemical equation and break it out. This is gasoline. So I'll write that up here. So gasoline, now gasoline is kind of a funny fuel because it's actually a lot of different compounds mixed together. It's not like one specific chemical component. It's a bunch of different things. But is fairly closely represented by this molecule, C8H18. So 8 carbon atoms and 18 hydrogen atoms mixed together. That's what that fuel molecule would look like. Okay, so that's the fuel that we're putting in the engine. We need to mix that with some oxygen for this reaction to occur. But when we add oxygen, we're also adding nitrogen into that chemical equation. So here's the fuel, here's the air. So these two components together is the air. So this is the air, this is the fuel. That's going to react in there, and I'm going to put the word heat up here because we have a lot of heat that is happening, and that's going to be important when we come back and look at our emissions and look at some of the bad gases that are formed in there. So there's some heat, and that's going to end up as CO2, carbon dioxide, and water, H2O, and that nitrogen, hopefully, and in an ideal world, whatever goes in is going to come out. So because it's not part of that reaction, so we should have the same amount going in as we have coming out. Okay, so this is our basic equation, but it's not balanced, so we're going to have to balance this equation. How many of oxygen molecules do we need? How much nitrogen molecules are going to be going with that? How much CO2, how much H2O do we end up with out here? So this is going back to basic chemistry. How do we balance equations? And these equations, the nice thing about these combustion equations is they're always pretty much the same form when we're looking at the basic combustion chemistry. We have the fuel molecule, we're adding oxygen to it, we're getting carbon dioxide, and we're getting water, and then we have this nitrogen that's floating through. So here's the steps that I like to attack these things to make this happen. So what I do is look at the carbon atoms first. I look at how many carbon atoms I have on the left-hand side, and I see how many carbon dioxides I'm going to need on the right-hand side to balance that. So I go carbon from left to right, first step. Then I do hydrogen from left to right. That's my second step. See how many hydrogens I have over here and how many I'm going to need over here to balance that out. So carbons go from left to right, hydrogens go left from right. Then I'm going to see how many oxygens I'm going to need over here to make this carbon dioxide, to make this water. So I'd figure out how many oxygens I have on the right-hand side, take them back to the left, and see how much I need over here. So the oxygen then goes from right to left. Okay, so carbon left to right, hydrogen left to right, oxygen right to left. We go backwards. And then when we're done, we're going to figure out how many of the nitrogens that I'm going to need, or how many is going to be coming along with that oxygen when I pull that air into the engine. So those are the steps we do. So let's tackle that on this one. So first of all, let's look at the carbons. So where do I have carbons on the left-hand side? The only place I have carbon is in the fuel molecule. So this is pretty easy. How many do I have? I have 8 right there. So how many carbon dioxides am I going to need? The only place I have carbon on the right-hand side is the carbon dioxide. So if I got 8 carbons here, I'm going to need 8 CO2s right here. Okay, so I put 8 in front of the CO2s, and that's how many carbon dioxides I'm going to need. 8 right there. Okay, so that's the carbon from left to right. Now let's do the hydrogen. How many hydrogens do I have on the left? The only place I have hydrogen is in the fuel molecule. There's nothing, and again, there might be some trace amounts of that in the air, but it's not enough for us to bother counting. So there's 18 of them here, so I've got 18 hydrogens. How much water do I need? Well, now I look at the water, and each water molecule has 2 hydrogens in it. I need 18 total, so how many water molecules I need? I need 9 of them. So 9 times 2 is 18, so this gives me 18 total hydrogens on the right-hand side. Again, each one of these water molecules has 2 hydrogens in it. So 9 times 2 is 18. 18 over there. Hey, I'm good to go. Now, next step. I did the carbons, I did the hydrogens. I got to take the oxygens back to the left. So I need to look at how many oxygens I have on the right-hand side of the equation. So let's look through this equation, see where I have oxygens. Looking through the right-hand side, I've got oxygens in the carbon dioxide. So let's write this down. How many do I have? I have 8 molecules. Each molecule has 2 oxygen atoms in it. So what am I going to have is 8 times 2. That's how many oxygens are in that carbon dioxide. Where else do I have oxygens? Oh, I have oxygens in the water. Each water molecule has only 1 oxygen in it, so this is a 1-to-1 relationship. So it's add to that plus 9 oxygen molecules in the water. And I could say 9 times 1 if I wanted to, since there's only 1 in that. So what is that? 2 times 8 is 16, plus 9 is 25. So that means I have 25 oxygen atoms on the right-hand side of the equation. So now I got to go back to the left-hand side of the equation and say, how many oxygens do I need over here then to make this happen? So I need 25. That oxygen is all going to be coming from, in this particular reaction, it's all coming from the air. It's coming from these O2s. So I need 25. How many molecules do I need? Well, it's not going to come out right because this is an odd number and this is factors of 2, right? So if I had 12 of these, that would give me 24. 12 times 2 is 24. If I had 13, that would give me 26. That's too many. I need 25. So what do? I do a half in there. Okay, so I'm going to say that I need 12.5 oxygens to make that happen. Now, chemistry purists are going to say, oh, you can't have a half of a molecule of oxygen. So what they will make you do is say, okay, now you got to make 2 of these. You got to start up here with 2 of your fuel molecules, which is going to double all these other things so that you come back up here and it works out. I'm not going to get real fussy about that as long as we keep track of what it is. So I'm okay with us working with fractions in here, decimal numbers, non-integer numbers over there. So it's going to, for our intents and purposes, what we need to do, we can, as long as we keep track of that, and we'll see how we'll use that later to calculate our air-fuel ratio. So that number will be important. Okay, so we can do that. We can deal with 12.5. So 12.5 times 2 is 25. So now my oxygens balance from left to right. Okay, so we did the carbons, we did the hydrogens, we did the oxygens. Next thing we got to do is figure out how many nitrogens come over. Remember that relationship that I mentioned to you is that the number of nitrogen atoms is equal to 3.76 times the number of oxygen atoms. Okay, so how do we do that? And the number of N2s is equal to 3.76 times the number of O2s. How many O2s do I have? I have 12.5. So this is 3.76 times 12.5. And that equals to, and we got to run the calculator, and here's where we could get really ugly with the chemistry purists. It could get kind of nasty sometimes, but in this case it actually works out fairly round number, and that's 47. So what that's telling me is that I'm going to have 47, I'll write 47 up in the equation, 47 nitrogens that are nitrogen atoms that are going to be, or nitrogen molecules that are becoming with the oxygen going into that engine, and hopefully nothing happens to them, and they're going to come out in the exhaust as just 47 N2s, okay, 47. And now my equation is balanced, okay? You see how to do that? So carbons, hydrogens, oxygens going back, then calculate the nitrogens, and we're good to go, okay? Let's do another example so we know what's going on. This one's going to be a little bit different. So this was gasoline. So the next example we're going to do is ethanol. So this is if we were using pure ethanol in an engine. So ethanol is a little bit different. So if you look at the molecule of ethanol, it's got some carbons, it's got some hydrogens, not near as many, but it also has an oxygen in it. And we'll see later how we've talked about an oxygenated fuel when we talked about fuel properties, that we add things to ethanol because it is an oxygenator. It adds oxygen to the fuel, and this is going to help us in our combustion process. We'll see later how that really happens. But notice this one has some oxygen in it. Okay, so again, we set up this equation. It's very simple. Whatever the fuel is, we put it here. We're going to react with that fuel some oxygen. So we know we're going to add oxygen. So we're going to take the fuel plus O2 plus N2 because the nitrogen is going to come with it as it goes into the engine. That's just part of the air that comes in. And what comes out? Right-hand side of this equation is always the same. CO2, H2O, and some of that nitrogen out there. This is that ideal reaction equation, okay? So let's build this up and let's do this. So what is our steps again? I'll write them down so we remember. So the carbon goes from left to right. The hydrogen goes from left to right. Oxygen goes right to left. And then I do my nitrogens last once I know how many oxygens that I need. So let's go through this process. How many carbons do I have on the left? If I look at my carbons, the only place I have carbon is in the fuel atom. So that goes over to the carbon dioxide on the right. So how many do I need? I have 2 on the left. I need 2 CO2s on the right. So that one, pretty much you carry that the number there, the number of carbons straight over, and that one's pretty easy. Hydrogens, I got to watch a little bit. How many hydrogens do I have on the left? Hydrogens over here in the fuel, I've got 6 of them, and I need to know how many waters I need on the right. So every water has 2, so 6 divided by 2 is 3. So I need 3 water molecules. 3 times 2 is 6. That's 6 on the right, 6 on the left. I'm good to go, okay? So oxygens now. What do I have on the right? Let's calculate it out. I have 2 oxygens in my carbon dioxide, so I have 2 times 2 carbon dioxides, times 2 oxygen atoms in each one of those, so 2 times 2, plus how many waters do I have? I have 3 waters, and there's 1 in each water molecule, so that's plus 3. So 2 times 2 is 4, plus 3 is 7. So I'm going to need, I have 7 oxygens on the left. So how many oxygen molecules do I need? Or that's what I have on the right. I have 7 on the right, so how many oxygen molecules am I going to need on the left? So let's look at this oxygen molecule right here. How many do I need? I need 7 on the left, but keep in mind, I have 1 already in that fuel molecule. So there's already 1 on the left. So I don't need as much air going into this thing because I've got some oxygen in the fuel. So I have 1 in the fuel. I need 7 total on the left-hand side. So that means this oxygen molecule is going to have to provide 6 of them. So to get 6 of them, each one of those is 2. So I need 3 oxygen molecules on the left-hand side. So 3 O2s are going to give me that. So again, you got to be careful on this. Let's look at this equation. 3 oxygen molecules here. 3 times 2 is 6. Don't forget about this 1 in the fuel, plus 1 is 7. So there's 7 total on the left-hand side of the equation. How many on the right-hand side of the equation? 2 times 2 here is 4, plus 3 more is 7 on the right-hand side. So that's the thing that a lot of people will make mistakes on. So be very careful when you calculate this on the right-hand side and go back. You don't necessarily need all of them with the free oxygen. There might be some oxygens in that fuel molecule. So make sure that you don't forget about that fuel molecule and multiply that out. Okay? So there's my oxygens. I've got the oxygens from right to left. So let's look at the nitrogens then. So again, the number of nitrogens is equal to 3.76 times the number of oxygens, of O2s. This should be N2 on the left. So 3.76 times, I have 3 O2 molecules. So that gives me 11.3. So what that tells me is in my equation, I need 11.3 nitrogens going in. Hopefully then I will have 11.3 coming out on the back side. And here you can see where we could really have a big headache if we needed to balance this equation and make them all integers, whole numbers. So that would mean, oh gosh, I'd have to take 11.3, I'd have to multiply everything by like 3 or 5 or something like that, you know, to really make it work. So that we could spend a lot of time doing that. And again, I'm okay with us dealing with just these fractional numbers in here, and because we're going to use them then to calculate. So the next thing we're going to do, now that we understand how to build this equation, is we're going to look at air-fuel ratio. So we've talked about what air-fuel ratio we need for an engine, how much air in relation to how much fuel goes into the engine, and I'm going to show you how to calculate that from this equation.